Every time you pull off a woolen sweater in the dark and see a spark, you are witnessing electrostatics in action. This study of charges at rest traces to the ancient Greek word for amber, electron. Benjamin Franklin's experiments established a formal classification for these interactions, naming the two distinct types of charge, positive and negative. These interactions follow the Lara memory trick. Like charges move apart, while the reverse, unlike charges, attract. Rubbing a glass rod with silk makes the glass positive and the silk negative. This friction is simply a transfer of electrons. This rubbing action never creates new charge. It is an exchange, meaning the total number of electrons between the two materials remains constant. Every dramatic static phenomenon we see is the result of these microscopic, subatomic electron transfers occurring on a macroscopic scale. Materials are defined by how they respond. In conductors, such as metals or in the human body, electric charges flow freely through the material structure. Insulators, like plastic, glass, and wood, behave differently. In these materials, charges are effectively immobile, remaining locked in the specific spot where they were placed. This distinction explains a common board exam question. Why does a plastic comb get electrified when used, while a metal comb does not? Because both the metal and your body are conductors, any charge the comb picks up instantly leaks through your hand to the earth. A plastic comb retains electrification because it is an insulator, trapping transferred electrons in place. An object's ability to hold a static charge is dictated by its atomic structure and whether it is physically isolated from the ground. To solve numerical problems in electrostatics, we rely on three pillars of charge behavior: additivity, quantization, and conservation. Additivity treats total charge as the simple algebraic sum of all individual charges in a system, calculated exactly like real numbers. Conservation dictates that the total charge of an isolated system remains constant. Even in nuclear reactions, charges are only redistributed, never created or destroyed. This intricate laboratory setup proved quantization. It demonstrates that charge is not a continuous fluid, but exists in discrete, indivisible packets based on the electron. This is expressed as Q equals NE. Since the elemental charge E is exactly 1.6 times 10 to the negative 19 coulombs, it cannot take fractional values. You can have 2 electrons or 3, but never 2.5. Because this elemental charge is so small, 1 full coulomb of charge is massive, equivalent to roughly 6 times 10 to the 18 electrons. This is precisely why most exam problems rely on microcoulombs. Establishing that charge is discrete, indestructible, and algebraically additive is the mandatory prerequisite for calculating the forces between them. Coulomb's law provides the mathematical framework for determining the magnitude and direction of the force between two resting charges. This law states that electrostatic force is directly proportional to the product of the charges and inversely proportional to the square of their distance. This means if you double the distance between charges, the resulting force drops to exactly 1/4 of its original strength. In its scalar form, the equation is F equals K times the absolute value of q₁ q₂ divided by r squared, where the constant K is 9 times 10 to the 9th. While gravity is the dominant force on a galactic scale, the electrostatic force is stronger by a ratio of 2.4 times 10 to the 39th. This immense force is what maintains the proximity and arrangement of particles inside every atom. In systems with more than 2 charges, we apply the superposition principle, which states that the net force on any charge is the vector sum of all individual forces acting upon it. Crucially, the specific interaction between any 2 charges remains completely unaffected by the presence of a third. Each pair interacts as if they were alone in the system. Because these are vectors, you cannot use simple scalar addition. You must resolve the direction of each force before finding the total. For an equilateral triangle with identical positive charges, we analyze the top charge independently. The bottom left charge creates a repulsive vector up and right. The bottom right creates another up and left. By the parallelogram law, horizontal components cancel, leaving a vertical resultant force of √3 kq squared over L squared. Solving these problems requires the simultaneous application of Coulomb's law and precise geometric vector resolution. Coulomb's law describes the force, but it doesn't explain how a charge knows another charge is far away without physically touching it. This 19th century portrait of Michael Faraday represents the shift toward the electric field, a concept that explains how charges interact across empty space. We define the electric field as the force exerted per unit positive test charge. A source charge fundamentally alters the space around it. When a test charge enters that space, it simply responds to this modified environment, rather than reacting to the distant source charge directly. This test charge must be infinitesimally small. If it carried significant charge of its own, it would disturb the very field it was meant to measure. In this model, charges don't reach out to pull one another. They react to the invisible map of the electric field already present in their location. We visualize this invisible map using electric field lines. For quaint charges, the rules are rigid. Field lines always push radially outward from a positive charge and pull radially inward toward a negative charge. In multi-charge systems, these lines bend away from like charges and towards unlike charges. Because the field is unique, they never cross. Accurate field line diagrams prove a complete understanding of how these invisible forces are distributed throughout physical space. To solve every problem in Chapter 1, you must master these 5 foundational equations. They cover quantization, force between pairs, field strength, and the force on a charge within a field. These formulas, paired with the Lara and AQC memory anchors, provide the framework for every calculation in this chapter. For a final knowledge check, what is the correct SI unit for the electric field? The correct answer is newtons per coulomb, or volts per meter. Mastering these invisible properties and the vectors that define them has built a clear, functional foundation for the rest of physics.